Welcome to this explainer. Today, we're unpacking something absolutely crucial, the exact architectural framework scientists use to describe reality. We're going way beyond the basics here to lock down the strict definition of physical quantities. It's basically the foundational vocabulary that drives all scientific inquiry. Let's get right into it. So, what exactly is a physical quantity? Well, simply put, it's something that can be measured, and it's what we use to describe the laws of physics. Think about a group of runners in a race. We can't just stand there and casually say, wow, they're fast. I mean, that doesn't really help us do real science, right? To actually do the science, we have to quantify that motion using specific, measurable properties, things like distance, time, and speed. That is exactly how we turn a simple observation into rigorous physics.
Okay, here's our roadmap for today. First, we're going to look at fundamental versus derived quantities. Then, we'll tackle the system of units, followed by dimensions of the world. And finally, we'll wrap things up by looking at scalars and vectors.
Right, let's dive straight into Section 1, fundamental versus derived quantities. A great way to think about measurements is to compare them to the letters and words of an alphabet. On one side of the coin, you've got fundamental quantities. These are your absolute baseline, kind of like individual letters. They stand completely on their own and just cannot be expressed in terms of anything else. But then, on the flip side, we have derived quantities. These are essentially the complex words and sentences that are built entirely by combining those solitary, fundamental building blocks. And here they are. These 7 base quantities act as our definitive physics alphabet. We're looking at length, mass, time, electric current, temperature, luminous intensity, and the amount of substance. Every single thing we can possibly measure in the known universe, literally no matter how wild or complex the phenomenon is, traces its lineage directly back to these 7 foundational blocks. It's kind of mind-blowing when you think about it. So, just as letters combine to make words, our fundamental quantities multiply and divide to create derived ones. Take a look at velocity. It's simply displacement, which is a length, divided by time. Then acceleration takes that velocity and divides it by time again. And force? Well, that takes mass and multiplies it by acceleration. We're literally just mixing and matching our fundamental alphabet to decode more and more complex physical interactions. Moving right along to Section 2, the system of units. Now, identifying a physical quantity is really just step 1. Once we have it, we absolutely must have a standardized way to express its magnitude. That's where a unit comes in, an arbitrarily chosen standard of measurement for quantity that's accepted internationally. Because, honestly, the whole process of measurement is just a process of comparison. If I tell you a rope is 10 meters long, what I'm actually doing is proving that this specific rope is exactly 10 times as long as our universally accepted 1-meter reference standard. Without that agreed-upon standard, the number 10 means absolutely nothing. To really wrap your head around why these universally accepted units are so incredibly critical, just consider the mass of a single electron. We're talking 9.11 times 10 to the negative 31 kilograms. It's unfathomably tiny. Physics requires us to measure scales from this microscopic level all the way up to entire galaxies. Without incredibly strict, rigid measurement standards, trying to quantify this massive range would just be total scientific chaos. And establishing these standards comes with some pretty fascinating history. For over a century, a literal physical object, a platinum-iridium cylinder kept locked away in a super safe vault near Paris, defined exactly what 1 kilogram was for the entire planet. If your measurement matched that cylinder, boom, you had a kilogram. It just goes to show that defining physical quantities requires anchoring them in a shared, standardized reality. All right, let's shift gears to Section 3, dimensions of the world. I like to think of dimensions as the raw DNA of a physical quantity. Ask yourself, what happens if we strip away the specific unit, like forget about meters or inches, and just look purely at the structural nature of the measurement? Well, that's exactly what dimensions do. They show us which base quantities are required to represent a property, completely regardless of the unit system you're using. We denote these foundational dimensions using square brackets. So you'll generally see M for mass, L for length, and T for time. Finding a dimensional formula is this highly satisfying, deeply logical progression that reveals exactly how a derived quantity is put together. Let's use velocity again as our example. Step 1, we write out the basic formula, displacement over time. Step 2, we substitute our base dimensions. So displacement is a length, that's L, and time is T. We get L divided by T. Finally, step 3, we write the final dimensional formula. Since there's no mass involved here, M is raised to the power of 0. L is to the power of 1, and since T is sitting in the denominator, it's raised to the negative 1.
So our final dimensional DNA for velocity is m0, L1, t-1. Pretty neat, right?
And that brings us to our final stop, Section 4, Scalars and Vectors. So, as it turns out, not all physical quantities are created equal when it comes to navigating space. A scalar quantity simply tells you how much. It's just magnitude. Think distance or mass. A 70-kilogram mass is exactly 70 kilograms no matter which way you face. Direction doesn't matter at all. But a vector quantity, that tells you how much and which way. Things like displacement, force, and velocity absolutely demand a direction to be completely defined. When you're out there dealing with real-world phenomena, things like motion and forces, vectors become absolutely essential. You can't just know how hard you push something. You have to know exactly which direction you're pushing it. All these quantities, force, velocity, displacement, the position vector, acceleration, linear momentum, they all demand a direction. Why? Because predicting the outcome in physics requires knowing precisely where all that energy is directed. And notice how inextricably linked these concepts become. There's a great principle here. The direction of momentum is also in the direction of velocity, and the magnitude of momentum is equal to the product of mass and speed of the particle. What this beautifully illustrates is that the linear momentum of a particle isn't just about its mass and speed. Its direction is permanently bound to the direction of its velocity. In the world of vectors, physical properties are permanently tied to their actual trajectory through space. Which leaves us with this final, kind of brain-bending thought. Think carefully about all the definitions we've explored today. If you drive a car at a perfectly constant speed, say exactly 30 miles per hour, but you turn a corner, does your velocity change? Well, the answer is a resounding yes. Because velocity is a vector, a simple change in direction alters your physics entirely, even if your speed stayed exactly the same on the dashboard. And that brilliantly proves why defining physical quantities precisely isn't just some boring exercise in semantics, it is literally the key to decoding the rules of reality. Thanks so much for joining me on this explainer. I really hope it gave you a totally new lens through which to view the physical world around you. Catch you next time.